students, welcome again. I am Mr. Mohammad Sabaj Alam, Assistant Professor in ABES Engineering College. In the previous lecture, I have discussed the working of transistor and VI characteristics of common base configuration. Now, in this lecture, I am going to discuss the common emitter configuration and some numericals, example of numericals, that how we will solve the circuit of common emitter configuration if we need to calculate some current, terminal current and terminal voltages. Now, common emitter configuration, as discussed earlier, that if emitter terminal is taken as common for input as well as output, that connection or configuration is called common emitter configuration. In the same way, emitter is taken as ground, that is reference terminal, and input terminal is base and output terminal is the collector. This means emitter is the common terminal here. This is the NPN transistor and this is the VCC and this is the VBB. We have connected like this. Here, since collector terminal is the output terminal, so that IC current is called the output current. On the other hand, since base terminal is the input terminal, so that the base current is the input current. Now, the current gain of common emitter terminal is common emitter configuration is represented by the beta. Now, beta DC is defined as the output current upon input current, that is IC upon IB. IC is the output current and IB is the input current. In the same way, beta AC is defined as the change in output current upon change in input current, that is delta IC upon delta IB. The value of beta is greater than alpha. Why it is like that? Because the order of base current is in order of microampere, because this is the recombination current, and recombination current is the very small value, because it is the recombination current and this is the collector current, and collector current is in order of milliampere and base current is in order of microampere, so that the value of beta is greater than alpha. Now, relation between alpha and beta. We all know that alpha is the current gain for common base configuration and beta is the current gain for common emitter configuration. Now, we know that IE equal to IC plus IB. In any transistor, any configuration, this relation is the universal relation, that emitter current is equal to the sum of collector current and base current. Already we have seen in the working of transistor. Now, if we will divide this equation by IC, what will happen? That IE upon IC is equal to 1 plus IB upon IC. What is this? This value is the this value is the 1 upon alpha and this value is the 1 upon beta. 1 upon beta. This means 1 upon alpha is equal to 1 plus 1 upon beta. If we will rearrange this, we will get that alpha is equal to beta upon 1 plus beta and beta is equal to alpha upon 1 minus alpha. This is the relation between alpha and beta. This means the value of alpha is less than 1 and the value of beta is greater than 1. Okay, guys. So, we need to remember the relation between alpha and beta. Suppose we will apply this relation to solve a numerical. Let question, suppose IC is given IC is equal to, suppose 10 milliampere and here alpha is given 0.98. Okay, guys. Then we need to calculate IE is equal to what and beta is equal to what and IB is equal to what. Then how we will proceed? Now, solution. First of all, if alpha is equal to 0.98, then what will be the value of beta? Beta is equal to alpha upon, that is 0.98 upon 1 minus 0.98, and this is equal to 49. Okay, guys. Now, what will be the value of IE? IE is equal to IC upon IC is given, then alpha IC upon alpha, and IE this is equal to 10.204 milliampere. Now, we have the value of IE and we have the value of already IC, then what will be IB? IB is equal to IE minus IC, and this will equal to 10.204 minus 10, that is this is equal to 0.204 milliampere. So, guys, this is the application of alpha and beta. Now, leakage current in common emitter configuration. Obviously, already we have discussed that how we will calculate or how we will observe the leakage current. To observe the leakage current or to know the leakage current, we must to open circuit the input terminal. If base terminal is here, input terminal, since base is open terminal, open circuited, then what will be here? A current is flow in between collector to emitter, and this current is called the leakage current of common emitter configuration and represented by the ICEO. ICEO, this means collector to emitter current when base terminal is open. Now, what will be the total current? Now, total current, that is collector current, is equal to beta IB plus ICEO. Beta IB is the current, majority current, and ICEO is the current due to the minority carrier. So, the total current is equal to IC equal to beta IB plus ICEO. Now, we have to derive the relation between ICBO and ICEO. How we will derive the relation between ICBO and ICEO? ICBO is the leakage current of common base and ICEO is the leakage current of common emitter configuration. Sometime this relation is being asked in the examination, that what is the relation between the ICBO and ICEO. It is quite simple, that we know that IC equal to alpha IE plus ICBO. This is the main equation of common base configuration. Already we have discussed it. Now, IC is equal to alpha IE. Now, IE may be written as IC plus IB. This means alpha into IC plus IB plus ICBO. Now, we have taken alpha IC at the left side and taking the IC common, then we will get IC into 1 minus alpha is equal to alpha IB plus ICBO. Now, IC equal to alpha upon 1 minus alpha into IB plus 1 upon 1 minus alpha into ICBO. Then what is this? Alpha upon 1 minus alpha is the beta. This is beta, and this means IC is equal to beta IB, and 1 by 1 minus alpha, if we can easily, if we will eliminate the alpha, that is beta upon 1 plus beta, then we will get the value of 1 upon 1 minus alpha is equal to 1 plus beta. This means this is 1 plus beta plus ICBO. This is the equation 4. If we will compare the equation 4 with the equation 2, what will we get? We get that ICEO is equal to 1 plus beta ICBO. This is the relation between ICEO and ICBO. This means ICEO is the 1 plus beta times ICBO. This means in case of common emitter configuration, leakage current is greater than that of common base configuration. Now, this is the relation between the two leakage currents. Now, I am going to discuss the VI characteristics of common emitter configuration. To discuss the or to draw the VI characteristics, this means input and output characteristics of common emitter configuration, we need to design an experimental circuit. So, this is the experimental circuit of common emitter configuration, and we need to connect 4 meters, 2 meters each for input to measure the input parameters and 2 meters each to measure for the output parameters. That is 2 voltmeters are there and 2 ampere meters are there. This is the microampere meter, and it will measure the base current. It will measure the base current IB. This will measure the IB. And here a voltmeter is connected in between the base terminal and emitter terminal. This will measure the VBE. On the other hand, another ampere meter in order of milliampere, that is milliampere meter, is connected here to measure the output current IC, and voltmeter here it connected here in between collector and emitter, that is in parallel. It will measure the output voltage, that is the voltage between collector and emitter. Now, this is the connection. When we will write the observation table, suppose we will write the value of VBE and IB, then we will keep this value constant. We will constant the rheostat here. This means the VCE must be constant. Then we will take the readings of these 2 meters for full scale. On the other hand, when we will taking the readings of these 2 meter, we will keep the IB base current constant, and we will take the various readings of these 2 meters. Now, I am going to discuss the input characteristics. Obviously, the input characteristics will be drawn in between the input current and input voltage. Now, input current is the VBE and input current is the IB, as shown in the figure here. IB is the input current and VBE is the input voltage here. So, this is the characteristics. Now, suppose I am drawing the input characteristics in between VBE and IB at VCE equal to 1 volt. I am taking VCE 1 volt here. This means my graph slope is more. If somebody drawing the input characteristics taking VCE 10 volt, then his slope is less than that of my graph. Now, if third one draw the input characteristics taking VCE, that is output voltage 20 volt, then his slope is least. This means what is this? If we are increasing the value of VCE, the slope of the graph increases. The slope of the graph increases. This means input resistance decreases. Why input resistance decreases? This means input current increases rapidly. This means what will happen like this? If VCE decreases, then the current increases and input resistance also decreases and input current increases. Why it is like that? I am going to discuss this phenomena basically. Here now, yes, I am going to discuss it. Suppose this is the 3 layers of transistor N, P, N. This is base layer, this is emitter layer, and emitter is grounded here. And this is forward bias, and this is reverse bias. Now, if this junction is in forward bias, this means the voltage between base and emitter must be 0.7 volt. And since it is emitter is at the 0 volt, this means base is at the 0.7 volt. Now, case 1, I am taking the VCE, suppose I am taking the 20 volt, VCE is 20 volt. Then what will happen? Collector is at the 20 volt. Collector terminal is at the 20 volt. Why VC is 20 volt? Since emitter is 0 volt. Emitter is at the 0 volt. This means the collector is at the 20 volt. Now, this means this junction is reverse biased with the voltage of 19.3 volt. This junction is reverse bias. The penetration of reverse bias is due to the 19.3 volt. Yes, 19.3 volt. This means the width of the depletion layer is more. This means the maximum portion of base layer has been depleted. This means base layer has least number of holes, least number of majority carriers. This means the base current, recombination current will be least. Since input current is least, this means input resistance is maximum. That is why for 20 volt the slope of the graph is least. Why least? Because input resistance is more. Now, case 2, if I am taking 10 volt, then this penetration of reverse bias will be 9.3 volt. This means the width of the depletion layer decreases. This means since width of the depletion layer decreases, this means the number of majority carrier, number of holes at the P layer will increase. If number of holes at the P layer or base layer will increase, this means the recombination current will also increase. If recombination current increase, this means IB current increases. This means the input resistance decreases, so that the slope of the graph will also increases as like this. The slope of this graph is greater than that of this graph. यानी 20 वोल्ट का वोल्ट पे जो ग्राफ का स्लोप होगा उससे 10 वोल्ट के ग्राफ का स्लोप ज्यादा होगा. Now, the third condition is for 1 volt. If we are taking this 1 volt, then what will be here? Then this junction will be reverse biased with 0.3 volt. 0.3 volt. This means in this condition the width of the depletion layer will be minimum and the number of majority carrier at the base layer will maximum. This means the recombination current will be maximum. Since recombination current, that is base current, is maximum, that is input resistance is minimum, so that the slope of the graph is maximum. So that if we are decreasing the VCE, this means if we are decreasing the collector voltage, then the input current increases and input resistance, this is the input resistance also decreases. And if we are taking VCE 0.2 volt, then the transistor become in saturation region. Why it will become in saturation region? I am going to discuss. Because for saturation region, this voltage is 0.8 volt and this means base layer is at 0.8 volt. And if we are taking this voltage, that this means voltage between collector and emitter is equal to 0.2 volt, then what will happen here? The collector point is at the 0.2 volt, Then what will happen here? The voltage difference between the P layer and N layer will become 0.6 volt, and in 0.6 volt the yani greater than 0.5 volt, the transistor junction become in forward bias. Since this junction will become in forward bias and the emitter base junction is already in forward bias, now the both junctions become in forward bias, that is transistors works in saturation region, and in this condition the transistor will not work as an amplifier. In this condition transistor will work as an switch, as an on switch. So, okay guys, already I have discussed the various conditions of the input characteristics. Now, I am going to discuss the output characteristics of common emitter configuration. Now, the output characteristics will be drawn in between output voltage and output current. Since IC collector current is the output current and collector to emitter voltage is the output voltage. Now, x axis is output voltage and y axis is output current. Now, it is the graph. Now, we can easily observe that at the higher current of output current, the slope of the graph changes. The slope of the graph changes, that is inclinedness will be increased, and at the lower value of the collector current, the graph is almost parallel with the x axis. Why it is like that? I will discuss it now. Now, first of all, I am going to define the output resistance. What is output resistance? R naught is equal to the change in output voltage upon change in output current. Now, that is delta VCE upon delta IC, but in this condition the base current should be constant, because suppose at base current equal to 20 microampere, I am taking 2 points. Now, what will happen here? If we will draw the perpendicular here and if we will draw the perpendicular here, this will be equal, this is called the delta VCE, and if we will draw the perpendicular here, this will call the delta IB, change in input current, and change delta, this is delta IC, delta IC, change in output current upon, and this is change in output voltage. Then output resistance is the ratio of change in output voltage and change in output current, but here IB remains constant, that is at 20 microampere. So that this is the value of the output resistance. Now, if we are moving upward, then what will be here? Suppose at 70 microampere, what will happen here? The change in collector current will increase. Change in collector current increase, this means the R naught decreases. Obviously, why R naught must be decreases at 4? Because if current increases, obviously the resistance decreases according to the Ohm's law. If current increases, then resistance must be decreases. So that it is the phenomena exist like this. Now, we can see the 3 regions here. Suppose the VCE saturation, this point is the VCE saturation, that is 0.2 volt. And from the left side of the 0.2 volt, this darkened region is called saturation region. This region is called saturation region, and the IB equal to 0, this means below the IB equal to 0, this darker region is called the cutoff region. Why it is cutoff region? Because IB is equal to 0, that is emitter base junction is open circuited, this emitter is open circuited, this means emitter base junction is in reverse bias and collector base junction is already in reverse bias. Since here both the junctions are in reverse bias, that is why transistor is in cutoff region, and in this region transistor can be used as an open switch. And now, at the left side, since VCE equal to 0.2 volt, since VCE equal to 0.2 volt, both the junctions are in saturation region. Already I have discussed in the previous slide, in the previous explanation, that when VCE equal to 0.2 volt, the transistor is become in saturation region. Now, on the other hand, here in between the cutoff region and saturation, there is a region, that region is called the active region. In this region, emitter base junction is in forward bias and collector base junction is in reverse bias, and transistor is used as an amplification, and this means this region of operation is the main region of operation, because the main application of transistor is the amplification action. Now, this is all about the explanation. Already I have explained all these 3 regions in case of common base, and all points are almost same. Now, I am going to discuss the transistor equivalent circuit. This is the transistor equivalent circuit. This is called VCE and this is called VBE. For active region, VB equal to 0.7 volt, and it is the this diode is called emitter diode, and this current is equal to beta DC into IB, because this current is the collector current IC. So, this is the equivalent circuit of the transistor, and this circuit will be very helpful when we will discuss the AC analysis of the transistor. Now, I am going to explain a simple example of common emitter configuration, that how we can apply the KCL, how we can apply the KVL, how we will calculate the terminal voltages, and this type of discussion will also continue when we will discuss the bias stabilization, but it is just the simple example. Just I have taken an example here. VCC equal to 12 volt and VBB equal to 5 volt and RC equal to 1 kilo ohm and RB equal to 100 kilo ohm. Then we need to calculate the value of VCE and we need to calculate the value of IC and we need to calculate the value of IB. We will discuss here. Now, what will happen? Here we have to calculate the VCE, IB and IC. So, then now I am going to calculate this value. Yes, suppose IB is equal to VBB minus VBE upon RB. Why it is like that? Because if we will apply the case KVL here, then what will happen? VBB minus IB into RB minus VBE, and this voltage already you know that 0.7 volt. Now, then IB equal to VBB minus VBE upon RB, that is 5 minus 0.7 upon 100 kilo ohm, this is equal to 43 microampere. Now, IB equal to 43 microampere, suppose beta is equal to 100, then what will happen here? Then IC equal to beta DC into IB, then this is equal to 4.3 milliampere. Now, I am going to discuss the VCE. Then VRC, this means voltage drop across this resistance VRC is equal to IC into RC, that is 43 milliampere into 1 kilo ohm, this is equal to 4.3 volt. Here the voltage drop across the RC is 4.3 volt, then obviously what will be the VCE? VCE equal to VCC minus voltage drop across this RC, that is 12 minus 4.3 volt. Now, here VCE equal to we can write VCE is equal to VCC minus IC RC, and this is equal to 12 minus IC RC is equal to 4.3 volt, then it will become here 7.7 volt. This is called VCE. So, in the same way we can easily solve this type of numerical easily. Now, the typical breakdown voltage of transistor rating, the VCBO equal to 60 volt, VCEO equal to 40 volt and VBEBO is equal to 6 volt. These are the breakdown ratings of the transistor. Now, this is the references, and thank you. So, already I have discussed the common emitter transistor. In the next lecture we will discuss the operating point and bias stabilization as well as the common collector configuration. Okay guys, see you again.